Okay, so 4.1 is all about special angles. So you're going to get introduced to the unit circle, which is the first little diagram you have there on page 4. You just have a whole bunch of diagrams, which is essentially things you need to be able to understand and some terminology that we need in order to really discuss the trigonometry that's involved in this unit. So the first picture that you have there is a unit circle. So and a unit circle is a circle with center at the origin and a radius of 1 unit. So on this unit circle, if we have our x and y axes labeled, then this is 1, this is 1, this is -1, and this is -1. So where it crosses each axis is 1 unit away from the origin, which is the center of the circle. Not in mind because it's a terrible diagram. A couple of other things we need to know about is you can see that there's a little triangle drawn there, and basically that triangle is drawn in the first quadrant. So 2 diagrams down you have a little quadrant diagram where up here in the top right, where x and y are both positive, that is our first quadrant. Then an angle always stretches around the unit circle counterclockwise. I'll explain that in a second, but for now you just need to know that this is your second quadrant. And it keeps going around to your third quadrant, where both x and y are negative, and then your fourth quadrant, where x is positive and y is still negative. We're going to be doing a lot of talk about angles. So you have another diagram right there, and you have an angle drawn, and you might want another color out, but basically this arm is a ray. So a ray is a line, like a line segment has a start and a stop. A line goes on forever. A ray has a start but no stop. A ray, in this case our ray starts at 0, 0 and goes on forever. That is the initial arm of our angle. We can take a little note on that. The initial arm is the first arm or ray of an angle. Drawn on a Cartesian plane. Have you ever heard the word Cartesian plane? Basically, this is a Cartesian plane. So we've called it a coordinate plane before, because coordinates, every point on the coordinate plane is represented by coordinates. So a coordinate plane. Plane just means a flat surface. Some guy whose name is, I don't know what his name is, but probably Cartesia or something like that, came up with the Cartesian plane. So the first arm or ray of an angle drawn on the Cartesian plane that meets the other arm at the origin. Now that other arm is called the terminal arm. So an angle will be made by the initial arm, which always goes along the horizontal axis, and it will end at the terminal arm. So we call this guy our terminal arm, and we can take a note. The terminal arm is the arm that meets the initial arm at the origin. And rotates around the origin counterclockwise. To form a positive angle. Okay, we're going to add to that definition in a second, but just to explain, so this terminal arm could be coming out anywhere, but it's moving counterclockwise, forming a positive angle. So right now this positive angle is what, about 55 degrees? Okay, if it kept going and the terminal arm lined up with the y-axis, that would be 90 degrees. If it kept going and it split this, then it'd be 135 degrees. If it kept going and it lined up right on here, it'd be 180 degrees. Okay, it keeps going, creating positive angles until you get to 360. And actually it can keep going and create angles that are bigger than 360, which would be just multiple laps around the origin. We can also move this thing counterclockwise, in which case it would form what kind of angle? Negative angle. Nice. It can rotate around the origin counterclockwise to form a positive angle, or clockwise to form a negative angle. Now, when it's drawn like our example is, with the initial arm on the x-axis and the terminal arm wherever it happens to be, this is called an angle in standard position. Angle in standard position. Jot that down. And this is the position of an angle, when its initial arm is on the positive x-axis. And its vertex is at the origin. Okay, so this is an angle in standard position, because the initial arm is along the positive x-axis and the vertex is at the origin. The vertex made by the initial arm and the terminal arm. Okay, the diagram that you have at the top has more than I talked about. It has, so if we look at it, we can see that if we have this, remember the initial arm is just along the positive x-axis, and here we have a terminal arm, okay, and it's 1 unit long, because we know the radius of our circle is 1 unit long. And if we took that terminal arm and we used it to draw a triangle, a right angle triangle inside our unit circle, okay, we'd end up with what you have in the diagram, where this length from the origin to where the right angle is represented by the letter x, and the vertical rise of our hypotenuse is represented as y. So the hypotenuse of any triangle that you draw within the unit circle has length 1 every single time, because the radius is 1. Okay? Now, this is a coordinate plane, so every point can be represented by coordinates. Well, it turns out that where the terminal arm meets the unit circle is represented by the coordinates cosine theta, sine theta. So that means that since you have, where are you writing this? If you can fit it by this diagram, that's fine. If not, then just write it somewhere down below. But maybe just also pay attention to what it means. So you could just add this to your top diagram. That's so far the only thing I've done, right? What that means is that this angle formed by the initial arm and the terminal arm is called theta. Okay, so it's just, theta is just a common name for an angle. You've seen it before, you'll see it again. But if I wanted to calculate the coordinates of this point, all I would have to do is for the x coordinate, I would have to type in my calculator cosine of theta. So for instance, we talked about this looking like maybe a 55-degree angle. Then all I would have to do is take the cosine of 55, and that would be the x value. That would be how far along from the origin we've moved in the x direction. And if I took the sine of theta, the sine of 55 in this hypothetical case, that would give me the vertical change from the x-axis up. Okay, and both of those numbers will be less than 1, right? Because the unit circle, the hypotenuse, is 1. So both of my legs are going to be less than 1 whenever I'm inside the unit circle, unless my angle goes right down. Anyway, this is called a reference angle. Okay? So we could take this triangle and we could take this arm and move it in different places. We'd always be able to come back to quadrant 1 and draw an angle that looks the same, but in quadrant 1 it's called the reference angle. We'll get into more of that in a second. On page 5, you have primary trigonometric ratios for special angles. So there are a whole bunch of angles that we're going to memorize their coordinates for them, because we can use those angles to get other angles. For instance, the angle 45 is related to the angle 135. So if you've memorized for example, if you've memorized these coordinates, well, how are they related to these coordinates? So this angle was 45 degrees. This big angle is 135 degrees. Well, what's same and what's different between the x-coordinate of this point and the x-coordinate of that point? If we're just looking at the x-coordinate, it's just the same number, same value, but it's negative. What about the y-coordinate between this point and this point? Just looking at the vertical the value vertically of this point and this point. They're exactly the same. Okay? So if you memorize the coordinates of this 45-degree angle, that means you can get this angle, you can get this angle, you can get this angle. Very easy, just by knowing which is positive and which is negative. Okay? Same is going to be true of 30-degree angles and 60-degree angles. And as we get better at it, there are angles in between that you can that you can form just by knowing the special angles as well. But anyway, I'm going to erase what I just drew, because you have a diagram that is just zoomed in on that first quadrant. And we have an angle that is 45 degrees. And they've drawn this out for you to create a right angle triangle. So now we have a diagram showing the unit circle, an angle of 45 degrees, and it's in standard position. It's in standard position because the initial arm is going out the positive x-axis, and the terminal arm has been rotated clockwise from there to create an angle of positive 45 degrees. Okay? Now, we're going to label a couple of points on it. We're going to call P the point where the terminal arm meets the unit circle. Okay, that's almost always going to be called P in our diagrams. This middle point, the origin, is going to be called O. It's always going to be called O in our diagrams. And this guy is going to be called N. I'm not sure why he's called N. But we're going to write a few notes. Since angle PON equals 45 degrees, and PN is perpendicular, see if I can fit this all on one line, to OA. See if we can say if that's true. A is going to be over here. So A is the point 1, 0. So we've got PN perpendicular to OA. Yeah? That's what allowed us to form a right angle triangle here. Then PON, triangle PON, is a right isosceles triangle. Okay, it's a right isosceles triangle. What they're saying is that ON has the same length as NP. Okay? ON has the same length as NP. We know that because a 45-degree angle would create a terminal arm that has a slope of 1. Right? So every time you go over 1, you're going up 1. Over 2, up 2. Over 3, up 3. Over 5, up 5. So no matter what you do, ON is going to be the same length as NP, which is what we're writing next. Then ON equals NP. So we're proving a theorem, and we'll understand it better when we get to it. Basically what we're going to get to is the length of each of these sides, okay, which is going to give us the coordinates of point P. So if we have this and we have a right angle triangle, we have a theorem that we can use in right angle triangles that relates the three sides together. Do you know what that is? Theorem that relates the side lengths of each side in a right angle triangle. Yep. Pythagorean or Pythagoras theorem. Pythagorean theorem. And from Pythagorean theorem, we know that one of the legs squared plus the other leg squared equals the hypotenuse squared. So we know that ON squared plus NP squared equals OP squared. But we know that NP and ON are equivalent. They're the same length. So we could rewrite this as ON squared plus ON squared equals OP squared, which means that 2ON squared equals OP squared. And what's OP in a unit circle? Hypotenuse in a unit circle. It's always going to be 1. So now we know that 2ON squared equals 1. Or 1 squared, which is 1, right? Okay, so how do I get the length of ON in order to get my coordinate, my x coordinate for the point P? algebra. How do we get ON by itself? I have to do the same thing to both sides, yep, but I'm not going to do any subtraction. I'm going to divide both sides by 2. That's going to give me ON squared equals 1/2. I don't want ON squared, I just want ON. What's my next step? The square root of both sides. So on the left, I'm going to be left with just ON. And on the right, I'll just write this and then I'll explain it to you in a second. Okay, so I wrote 1 over the square root of 2. You'll see this written a couple different ways. But whatever the case, inside here, if you did the square root of 1 over the square root of 1/2, okay? Well, that's the same as saying the square root of 1 over the square root of 2. Square root of 1 means you're finding a number that times itself equals 1. Well, 1 times 1 equals 1. So the square root of 1 is just 1. So it's 1 over the square root of 2. So if your brain did that, congratulations. If it didn't, there you go. That's how you go straight from this step down to 1 over the square root of 2. So, what do we discover? ON, which equals NP, equals 1 over the square root of 2. Therefore, the coordinates of P are 1 over the square root of 2, 1 over the square root of 2. I'll give you a second to make sense of that and review what we did and ask any questions if you have any questions. Okay, so we have the coordinates of point P. We know that if our terminal arm is meeting the unit circle, creating a 45-degree angle, then the x coordinate, the distance along the x-axis, is 1 over square root of 2, and the distance along the y-axis is also 1 over the square root of 2. And we have already written a note that says that the coordinates of a point, x is cosine of theta and y is the sine of theta. So we also know this. Hence, the cosine of 45 degrees equals 1 over the square root of pi, because the cosine of theta represents the distance traveled along the x-axis. Okay, the change in x is represented by cosine of the given angle. In this case, the angle is 45, and we know that when the angle is 45, ON is 1 over the square root of 2. Okay? We also know sine of 45. Since x and y are the same, then the cosine of 45 and the sine of 45 are also the same. So it's 1 over radical 2. And if we know that, then we also can say what the tangent of 45 is. Now, if you remember from your prerequisite skills, I think it was in there, how tangent relates to sine and cosine. Might not have been in there, but either way, I'll give it to you. The tangent of theta is equal to the sine of theta over the cosine of theta. Okay? It's the rise over the run. So in this case, tangent represents the slope in a certain way of talking, which is rise over run. So same thing here. Since sine represents the y coordinate, and cos represents the x coordinate, and we have rise over run with tangent, then we have y over x, which is the sine of 45 over the cosine of 45, which we know those specifically is 1 over radical 2 over 1 over radical 2. And whenever you have a fraction that has the same numerator and the same denominator, what's that equal to? Just equals 1. So the tangent of 45 is 1. Okay? What do you think the tangent of this is? This guy over here. If the tangent of 135. If the tangent of P is 1, then over here, one of our coordinates has become negative. The tangent will be negative over there. This will be negative 1. Down here, x will be positive and y will be negative. Tangent will be negative 1. Over here, x is negative and y is negative. So what's your tangent? Positive 1. Okay? We're making connections. This is, so we just described it for a 45-degree angle. That's the proof here. And I've kind of described how you can use it to find your other angles. Okay, so you know the cosine of 45 is 1 over radical 2, the sine of 45 is 1 over radical 2, and the tangent of 45 degrees is 1. And that's one of the special angles that you'll be memorizing. Okay, let's talk about the 30-degree angle and its multiples. So there you have a diagram. It's the unit circle again. Okay, it's the unit circle. And we've drawn an angle like that, and the triangle is finished off, and it's a right angle triangle, and you know the hypotenuse in a unit circle is always going to be 1. And so our goal, again, we can label all the same points. You have A at 1, 0. The bottom of that triangle, the right angle, is N. Origin is always called O. And the point where the terminal arm meets the unit circle is called P. And P has the coordinates cosine of theta, sine of theta. So this diagram shows a unit circle, the angle 30 in standard position. Notes. It's going to be very much like the last notes that we took. Since angle PON equals 30 degrees, add that to our diagram. 30 degrees. And PN is perpendicular to OA. OA being the initial arm along the x-axis. Then triangle PON is a 30, 60, 90 triangle. Right? If one of the angles is 30 and one of the angles is 90, the other angle must be 60. The interior angles of a triangle add up to 180. This part is a little bit trickier, and I'm going to start using different colors. That's a good idea. I'm going to explain it first, and then we'll draw it. By reflecting, familiar with what reflecting means? By reflecting triangle PON in the x-axis, so think about what it's going to look like. An equilateral triangle is formed. An equilateral triangle, and we'll name it. It's going to be triangle P. P is still going to be involved in it. O is still going to be involved in it, and then the other point is going to be P prime. Remember, if we ever moved a point or reflected a point, we could call it P prime. So P reflected is P prime, and that triangle is formed. In which And I'll stop there for a second. We'll draw it and then name all the points again. So here we're going to have this, I wish my circle were better, but it's going to look about like that, right? And this is going to keep coming down and meet there. And we call this point P prime. So now we've formed an equilateral triangle. How do we know that? Well, we know that this angle in the middle essentially got doubled, right? Now it's not 30, it's 60. And we know that this is 1 and this is 1. So it's an isosceles triangle, which means the two base angles must also be equal. The other key is that this one's called P and this one's called P prime. So they're the same angle, they're also 60. So 60, 60, 60. Okay? So here we're going to name all of our angles and just say that they are equal. So we've got angle POP prime. It equals angle OP P prime. And it equals angle OP prime P. So essentially we're just writing the three angles. We've got angle O, angle P, and angle P prime. And they all equal 60 degrees. Now what do we know about point N? Point N is still relevant. Tell me about point N. What is it doing now? It's not just where the triangles hit the x-axis. What word is missing? Midpoint. N is the midpoint of PP prime. Oops, no. Hence, P prime N equals Pn equals 1/2. Now how did we get to that? So by the angles, we figured out that it was equilateral triangle. Equilateral actually means equal length, right? Equal line, equal length. So if these hypotenuse guys were both 1, and it forms an equilateral triangle, then from P to P prime is also 1. Yeah? That length. Which means from N to P or N to P prime is 1/2. So we did all of that, doubling of this, reflecting of this angle into the x-axis. We did all of that just to find out that the length, the y coordinate here, is 1/2. Okay? Make sense? Kind of, ish. You're mad, but it's okay. Good. Okay. Now, same step as last time. We're going to apply Pythagorean theorem. Pyth, TH, if you know what you're talking about. And same situation, we know ON squared plus NP squared equals OP squared. And now we don't have that these angles are equal to each other at all, but we know the length of NP. What's the length of NP? It's 1/2. And we know the length of OP. Yeah. And we can reduce this. What's 1/2 squared? Top squared and the bottom squared. 1/4. Or you could say 1/2 of 1/2, right? 1/2 squared is 1/2 times 1/2, which is 1/2 of 1/2, which is 1/4. And 1 squared is just 1. Now we can rearrange to solve for ON. So we can subtract a quarter from each side. ON squared equals 1 minus 1 quarter, which is 3 quarters. And we can take the square root of both sides. I'm going to reduce right away. The square root of 3 is radical 3. The square root of 4 we can simplify to be 2. Therefore, the coordinates of P are, well, the x coordinate is ON, which we found out was radical 3 over 2. And the y coordinate is NP, which we found out was a half. So basically, on our diagram, there's not a ton of room. You might have more room than me. But this length from O to N, okay, is radical 3 over 2. And this length from N to P is 1/2. Okay? And what did that tell us? That gave us the measurement of, or the cosine, the sine, and therefore the tangent of this special angle. Special angle is 30 degrees. So we know that the cosine of 30 degrees, remember cosine is represented by the x coordinate, right? So the cosine of 30 degrees is radical 3 over 2. The sine of 30 degrees is represented by the y coordinate, is 1/2. And tangent of 30 is y over x, or sine over cosine. So it's 1/2 divided by radical 3 over 2. And if we're good with our algebra, you realize that dividing fractions is the same as multiplying the reciprocal. So really all you have to do is flip this 2. Well, the 2 goes into, how do I say this? If you're dividing a fraction, you're just multiplying by the reciprocal. So rather than 1/2 divided by this, we could go 1/2 times 2 over radical 3. Which would give you radical 2 times radical, which would give you 2 in the numerator and 2 times radical 3 in the denominator. I'm saying that wrong. Oh no, I'm saying that right. Ha, good. I'm going to just rewrite it proper. So that's saying 1/2 times 2 over radical 3, which is, the 2's cancel out, it's just 1 over radical 3. So the key to memorizing the unit circle is memorizing the sine and cosine of each one, and then getting the tangent by just putting sine over cosine. Okay? Did this part, I stuttered a couple times, but does that make sense to you? Okay? Okay, following the same logic as that previous one, you have a diagram that takes this 30-degree triangle and kind of reflects it over the line y equals x, okay, to create a new point P. And these triangles are exactly the same, okay? So it's reflected over the line y equals x. Is that already in your diagram? Yeah. Good. So the logic is exactly the same, but now it's swapped. So now we're talking about a 60-degree angle. So the coordinates of yep. Not me. The coordinates of P are the opposite of the last one. So now instead of radical 3 over 2 half, now it's half comma radical 3 over 2. Because all we did was we took the same length of x here and we flipped it up to be the vertical length. And we took the vertical length here and now it's the same as the horizontal length here. Okay? So the new coordinates are 1/2 3 over 2, which gives us the cosine of 60 degrees. Cosine relates to the x coordinate, so it's 1/2. The sine of 60 degrees is relating to the y distance from the origin, which is radical 3 over 2. And then the tangent of 60 is sine over cosine, which is radical 3 over 2 over 1/2, which if we multiply by the reciprocal, we end up with radical 3 over 2 times 2. The 2's cross out, and you're just left with radical 3 over 1, which is just radical 3. Okay, page 7, you have an investigation. Basically, we're going to be applying what we learned about special angles, the 45-degree angle and the 30 and the 60, to angles that are greater than 90 degrees. So we're going to head out of quadrant 1. First thing it says is label the intersection of the terminal arm and the unit circle. So we have our initial arm, we have our terminal arm. Here's where it intersects the unit circle. We're going to label that point A. And it says label the angle 45 degrees. So down here we show that we're working in a 45-degree angle. Reflect the point A in the y-axis to obtain the point C. So I'll use my ruler. Make sure I'm going straight across the y-axis. And if I reflect it, I should end up meeting the unit circle again. Right there. We're going to call that point C. The rest of point 3 says to join that point to the origin. Done. What is the measure of the angle between OC and the negative x-axis? So it's asking, here's O, the origin, right? It's asking what is the angle between here and the negative x-axis? It's also 45 degrees. This angle is referred to as the reference angle. Okay? So the reference angle is, we're not going to think of this as, okay, it's 135 degrees. It is, but it's easier for us to think of it as a small 45-degree triangle here. Reference angle. What are the coordinates of point C? Might help you to flip back and get the coordinates of point A. is 1 over radical 2, 1 over radical 2. So which of those coordinates becomes negative? The x-coordinate. So the x-coordinate is negative 1 over radical 2, and the y-coordinate is still positive radical 2. While we're here, we're actually going to take a note on this. What is a reference angle? Reference angle is, one sec, the acute angle between the terminal arm and the x-axis so the acute angle between the terminal arm and the x-axis of an angle in standard position. So OC forms an angle in standard position from here over. This becomes the reference angle, the angle between that and the x-axis. Okay? Yep. Okay, so now we can use the coordinates of point C to determine the cosine of 135 and the sine of 135. Which coordinate does cosine relate to? The x-coordinate. So the cosine of 135 is negative 1 radical 2, 1 over radical 2. And the sine of 135, 1 over radical 2. What about the tangent of angle 135? Well, we'd be doing sine over cos, which would be 1 over radical 2 over 1 over radical 2, and one factor is negative. So the tan of 135, so we have the same in the numerator and the denominator, it's just 1, but one of the factors is negative. So the tan of 135 is negative 1. Find the slope of the terminal arm OC. How does this slope relate to tan 135? So we're looking at this line. What's the slope of that line? We had this conversation earlier. It's just, well, yeah, 1, but it's going down. Yep, it's negative 1. So the slope of OC is negative 1. How does that relate to the tangent of 135? Same.